Okay, so welcome back to the machine learning for 3D data. So this is our third time to discuss some machine learning techniques for the 3D data. So last time we discussed some kind of the bunch of the representations of the 3D data. And we also discussed like why we need so many representations because each of them has some kind of the pros and the cons. So we discussed that the typical some kind of the very straightforward kind of extension from the 2D, some kind of the neural networks to the 3D might be using some 3D the grid. 3D voxels. So they might be good in terms of that we can easily extend all the ideas, like the convolution, many things, into the 3D voxels. The thing is that there are lots of the difficulties in terms of that the huge amount of the size of the data, right? In terms of that we're gonna have some very huge amount of the voxels, while most of the voxels will be the empty. So which means that we are basically having some very sparse information defined in the 3D space. So here the key would be is that how we can basically efficiently handle some kind of sparse data defined in 3D space with some kind of the specialized, some kind of the corners. So we can consider making some sparse convolution corners, whatever kind of things that might be also involving lots some kind of the engineering the efforts in terms of the implementations. So the issue with the voxels is that it's very hard to basically efficiently handle such kind of the representation of the 3D data. And the other way around would be basically just representing all these 3D things into the multi-view images. Then it becomes even easier to use some kind of a 2D neural network because we can just directly process all the kind of the multi-view images. But also kind of the problem is that it's also very inefficient kind of representation in terms of that we're gonna also need some lots of the images to precisely capture all the details, especially for some kind of the occluded the regions as well. We might need some lots of images that we can capture all the details. So efficiency is still kind of the issue with the multi-view representation. And then we also discussed the point cloud, the representation, which is the things that we're going to discuss for today, which is also very common representation that we can easily obtain from some kind of 3D scanning kind of the situations. And the good thing of the point cloud is that it's very basically easy to process and also generate using some kind of neural network. So what we are going to discuss for this week and the next week is about some kind of the neural networks that we can process and also generate the point cloud data. So we could also discuss about the efficiency of those kind of architectures. The downside is that point cloud also requires lots of some kind of the number of the points to capture all the details. So that's kind of the things in terms of the efficiency of like representing all the details of the some 3D information, the shape information, point cloud still may not be kind of the best representation. And speaking to this kind of the efficiency and the compactness, the mesh might be kind of the best representation in terms of that we can have the explicit the surface information. But then if we start to have some kind of the irregular, some kind of the mesh structure, it also becomes very difficult to process and also to generate some kind of the valid meshes. And the last representation we didn't get into the deep was basically implicit representation, which is basically representing the 3D shape into a deep function. And we are also going to get into the kind of the discussion about basically how we can also represent a 3D the shape into the implicit function after the discussion for the point cloud things. And after discussing like all different kind of representations, we also briefly, briefly discuss some kind of the conversion across those kind of representations. So what we could see is that the conversion from the implicit function into the voxel is also easy in terms of that we can just like evaluate the occupancy or many other things for each of the voxel. And also mesh it to point cloud is also very simple in terms of we can just like sample the points over the surface. Multi-view representation is just kind of simple from the mesh. If we just like render the 3D mesh into the images, and then the kind of the missing the bridges across those kind of representation is basically how we can also obtain the mesh from the other representation, and also how we can do some kind of conversion from the point cloud to the other representations. So those are kind of some more the challenging the tasks compared to the other kind of the convergence. So we are also going to get into the some kind of the ideas in terms of the how we can do kind of the conversion from the all the representations to the all the other representations. So those are also kind of the key things. But basically, what we can see from this figure is that point cloud is really kind of the good representation in terms of that you can easily obtain the point cloud from the any other representation into the point cloud, right? So in terms of that, if we want to process like the 3D data, for example, if we want to basically extract some kind of the information from the point cloud, like some kind of class of the objects or many other things, then it might be kind of like very efficient to first convert any kind of the 3D data represented into the any other representation into the point cloud first, and using some kind of the point cloud encoder. So that's what we are going to discuss for today. So the roadmap for this course is that we are going to basically discuss all different representations and also some kind of the neural net based some kind of the techniques that can basically either process or basically generate those kind of representations. So as I mentioned at the beginning, for this week and the next week, we are going to discuss the point cloud representation and also the encoding and decoding architectures for the point cloud. So we will see. So yeah, we are going to discuss the 2 point cloud encoders for today. And as I said, the reason like why we are discussing the point cloud is that basically for many kind of the some kind of applications that we are basically using some 3D scanning, the direct output from the 3D scanners will be point cloud. So that was kind of the first motivation in terms of like why we are basically investigating some kind of the architectures, processing the point cloud data. And also, as I mentioned at the beginning, the point cloud is kind of easy in terms of that it can convert from all the other into the point cloud representation. While the other way around is basically involving lots of some kind of computation and also requires the very dense the point cloud and also some kind of the extra information like the surface to the numbers. So we're also going to discuss some kind of the reverse conversion from the point cloud to the other representations. But that is basically giving some kind of motivation, like why we are basically more interested in basically the point cloud encoder, because like for even when you have some kind of the meshes or the voxels or any other representation, you can easily convert them into the point cloud and basically use the point cloud encoder. So that's kind of the motivation here. So the architecture that we are going to discuss for today is the simplest architecture. This is the very simple architecture, which is also kind of the very seminal work in terms of the 3D deep learning, which became some kind of the very basic the architecture that can be actually used also for the many other some kind of the applications. So we are going to start with like discussing this simplest architecture, and then we are getting into some kind of more complex the architectures. So basically, given this kind of architecture, if we first see what we are going to do using the neural network is that given the kind of the point cloud input, we are going to do these kind of the tasks. The first task is the classification. So given some kind of the point cloud describing some kind of the 3D object, we are going to see whether the given the object is a mug or the table or the car. So this is basically the classification task, right? So, and also we can consider doing some kind of the segmentation. So segmentation is basically indicating a subset of the points and see whether the points is some kind of the having some kind of the part label, like some kind of a chair or the table or the wall for some kind of 3D scenes. And also like leg and the top part of the tables. These are basically the parts of the objects, right? So we can either do some kind of the classification or the segmentation using the PointNet. So those are some kind of the tasks that we are doing. You can see that actually these are the tasks that we could see for the 2D deep learning, for the image basically neural network, right? For many kind of the image the deep learning the tasks, what we are going to do is that we are doing some kind of some classification or the segmentation. So the difference between these two is that classification is basically something that we are getting the information for the entire image, right? For the image case. While the segmentation is that we are getting the information per pixel, right? So those are some kind of the difference in terms of the output that what we want to see. So whether we're gonna get some kind of the output for the entire the image or whether we're gonna get some kind of the outputs for every single the pixel. And we're gonna do the same thing here. So we're gonna make some kind of the neural network that is giving some kind of the global information for the entire the point cloud, or also getting some kind of the local information for each of the single point. So we're gonna consider making this kind of the architecture that can handle both of the problems. So this is the problem, right? The problem is very simple. So basically what we are going to do is that we are going to consider that we are having some kind of the point cloud, which can be actually also can be seen as some kind of the 2D array representation. So let's say like we are having the n number of the points, right? And then each of the point we're going to have some kind of the d number of some kind of the numbers. Typically, we're going to have some kind of three numbers like x, y, z. Then these like the d dimension here becomes like three, right? But as I also mentioned in the last lecture, we can consider having some kind of the extra information, not only having the x, y, z, but we can, for example, like having some kind of the color information, like that RGB. And we can also have some kind of the surface normal information, then which is like adding another the x, y, z, basically the coordinates, right? So depending on some kind of the extra information, the dimension for each of the vector may not be three, it can be greater than three. But we are basically assuming that every point is represented as a the vector, and then we are having a list of the vector, which is basically becoming the point cloud, right? But here the thing is that while we are basically having some kind of the 2D array representation for the point cloud, what we want to achieve is that basically this is the set data, right? So we need to think about some kind of the characteristics of the set data. So when you say like the point cloud, which is a set of the points, the characteristics of the set is that we do not basically order those points. So which means that however we basically order the points, actually we don't treat them as some kind of a different point cloud. So the order of the points is basically not important. We don't care. So let's think about that. We are having some kind of the number one point, the first point, and the second point, and the third point. And we're gonna make this kind of the array like this. And let's say we shuffle the order of the points. Then should we get some kind of the different output for the classification? No, right? So whether we basically change the order of the points, actually it does not make some any difference in terms of like when we see the data as kind of the point cloud. So which means that the output should not be changed based on like how we order the points, right? So that's kind of the key characteristic in terms of that when you have some kind of a set data, the output should not be affected based on the basically the ordering of the data, based on the permutation of the data. So that's basically the kind of key characteristic that we want to achieve in our design of the neural network in terms of we are making the permutation invariance and the equivariance. So what we are also going to discuss the details of like this kind of term. And the one more thing is that we also want to achieve some kind of the transformation invariance, which means that, for example, like when you basically classify the objects like the airplanes here, however we rotate the airplane should be airplane, right? It does not also change the meaning of the given the point cloud, right? So which means that when the neural network takes this kind of the point cloud as the input, however we rotate this kind of the point cloud, the output should not be changed, right? So that's basically the characteristic that we want to achieve, and which we call that the transformation invariance, which means that however we transform the given the point cloud, the output should not be changed. So these are basically the two key things in terms of like, we want to achieve in the design of the neural network, like how we can make the neural network to give some kind of the consistently the same output, whatever the orders that we have for the points, and also having the same output also for the whatever the transformation that we are applying to the given the point cloud. So these are basically the two key things. It is clear? So let me first get into the specific meaning of the invariance and the equivariance. So when you also talk about the invariance and the equivariance, the difference between these two is that invariance basically means that however we change the index of the points, the order of the points, we get the same output. So for example, for the classification task, given a set of the points here from the x1 to the xn, we're gonna get the class label y, right? Or some kind of the probability for each of the class. So those are some kind of the global the output y here. And let's say now I'm basically changing the index of the points, basically shuffling the order of the points, right? Feeding them to the neural network. So our neural network is the function f here. So given the different order of the points, we want to achieve the same output y here. So that's the property that we call the invariance, right? Not making any kind of the changes depending on the given the permutation. Is this clear? Any questions on this? And equivariance is slightly different. This is for the case that we are basically getting some of the outputs for each of the data point, for each of the point in our case. So this is for the case of the segmentation, for example. So for the segmentation, we are going to get some kind of the label from the neural network, not for the entire shape, but for each of the point, right? So we are having the n points. We are also going to get the the labels. Each of them is basically corresponding to each of the points that we have, right? So this is the setup that we are basically having some kind of the same, the n dimensional of the output. Each of the element is corresponding to each of the point that we have. The segmentation is like example for this. And what we talk about the equivariance is that if we shuffle the order of the points, then now we are going to get the output, which is like having the same the shuffling of the order. Right? Makes sense? So if we change the order of the points, then the order of the output also should be changed based on the shuffling that we do, right? So this is the property that we call the equivariance. Basically some kind of changes that we are making into the input is also affected to the like making the changes for the output as well, making the same order. So that's the equivariance. So for the architectures that we are going to make, for example, for the classification, we are going to achieve the permutation invariance, making the output to be the same, not changed, whatever we do for the orders. For the architectures that we are achieving for the segmentation, we are going to achieve the property of the equivariance, making the order of the output is basically changed based on the order of the inputs. Okay? For the segmentation, should it also require transformation equivariance? So no, the transformation equivariance is for the it's more about the invariance, right? So basically, whatever we apply for the transformation, the output should not be changed, right? So that's why what we call that the transformation invariance, right? It is clear. So when you talk about the invariance, the equivariance, like whatever we do apply to the input, invariance means that we are not seeing any kind of changes in the output. Equivariance basically means that some kind of changes that we are applying to the input should also basically affect make some kind of same changes for the output as well, right? So we are also basically getting to permutation invariance and the equivariance. And for the transformation, we are also going to achieve the invariance. So whatever the transformation that you apply to the input, that should not affect the output as well. So if we can basically guarantee these two properties into our neural network, that will be really effective, efficient architectures in terms of that. So let's think about that. For example, like if we do not basically achieve some kind of the transformation, the invariance, what will happen? Can you guess? So let's say like we are basically making a neural network, which is basically classifying like the airplane or the chairs or tables or something, right? Making some kind of neural net. So we're gonna have some kind of a set of the like bunch of some kind of the airplane point clouds and the chair point clouds and the table point clouds, right? For each of them, you're gonna have some kind of the labels. So these are okay airplanes, these are the chairs, and these are the tables, right? Then we are training the neural network, right? And if we have a neural network, which is basically not satisfying the transformation, the invariance, then what will gonna happen is that the neural network will basically treat these 2-point clouds as kind of the different point cloud. So it's something new, right? So which means that if we train our neural network with the first airplane here, here, this one, and if we feed the second airplane as kind of input in the test time, then neural net will basically see that this is something new that I didn't see. I haven't seen it during the training, right? So there is no way that I can classify this. Basically, this is not the same, the point cloud as like something that we have seen, because like the neural network does not understand that the second one is not new. It's basically just like transformation for the first one, right? But without the transformation, the invariance, basically the neural network will basically treat these two as completely different, the point clouds. So which means that we need to basically show all this kind of some transformed versions of the point clouds in the training the time, so that the neural network can understand that these are all the airplanes from just like from the different some kind of the transformations, right? So this becomes like way more inefficient since the neural network is seeing these point clouds as kind of like all different kind of point clouds. We just need to show more examples. And also the neural net should have some kind of the enough the capacity to understand that these are all some kind of the different point clouds that should be classified into the airplane. But if the neural net basically have some kind of the capability of basically satisfying the transformation the invariance, then the neural net will see that actually these are just like same the point cloud. So even when the neural net is basically trained with the first one, the neural net will be able to see that actually the second one is the same point cloud. So this also should be classified as kind of the airplane. Make sense? Don't we consider invariance for the coordinate permutation? Yeah, so it's the same thing. Also for the permutation, the invariance, also if we do not satisfy this property, then if you basically change the order of the points, then neural net will see that this is kind of the new point cloud. Then which means that we need to train the neural net by just like shuffling the order of the points like all the time. This is basically like making all the different permutations of the point as the new point clouds. So that's the disaster, right? Because like you're gonna provide tons of the point clouds as in the training time to teach the neural net to see that actually these are all the same. But if the neural net basically have some kind of the property of the permutation, the invariance, then without really basically making the permutated the points in the training time, the test time, the neural net will understand that actually these are the same point cloud. So making the training to be way more efficient. Make sense? Any questions on this? So yeah, it's basically all about basically how we are making such kind of the neural network in terms of achieving the permutation, invariance, and the equivariance, and also the transformation, the invariance. So we can consider actually many kind of options for that. At the beginning, we are going to see some kind of the very simplest architecture for that. So specifically, this kind of function, which is basically achieving this kind of property. So when you basically achieve some kind of the permutation invariance, so when you change the order of the input data, if the outputs are basically the same, such kind of the functions are called the symmetric function. Okay, see, so let's say we have the like 1,000 points here. So when you change the order of them, if the outputs are guaranteed to be the same, such kind of functions are called the symmetric function. So let's think about the examples of the symmetric function. What would be such kind of some symmetric functions? Any ideas for this? Yeah, as many of you posted on the Zoom chat, yeah, these are all like the max, mean, average, like taking the norm, whatever, median. Yeah, these are all multiplication. Yeah, these are all the functions that are basically becoming some kind of the symmetric function, right? So to achieve some kind of the permutation, invariance, what we are going to do is that we are going to leverage this kind of symmetric function into our neural net design. So basically what we are going to do is that given any kind of the symmetric function, G here, we are going to make some kind of the more complicated the symmetric function using this kind of design. So let's think about that. When you have a asymmetric function G here, we can make another symmetric function F here by having any kind of arbitrary the H function and the gamma function here. See? So here basically you can see that H is the function which is basically processing every single point, but some kind of shared function, basically which means that the same function for all the points, right? So we are basically, for all the points, we are basically processing them using the same function H here. And using a given the symmetric function G here in terms of like getting some kind of the global the information and applying some kind of the post-processing the function the gamma here. So if we make some kind of the composition of the functions like this, given any symmetric function G here, we can say that actually this composition of the function also becomes another the symmetric function. Make sense? So for each of the point, we basically do some kind of processing with some kind of the, given the function h here independently, but the same function is basically being used for all the points. And then we are basically aggregating all this information using the symmetric function, g here. This kind of the process is typically called as kind of the pooling in the deep learning the literature, right? So we are basically having some kind of pooling operation and then post-processing this with some another kind of processing function here, right? Basically, then what we can say is that what would be some kind of typical choice for the h, g, and the gamma? I mean, it doesn't need to be some kind of the question. It's very obvious that we can have any kind of the function here, but we're gonna typically use some kind of the MLP, the multi-layer the perception for the function h here, and also the gamma here for the post-processing, while we are basically having some kind of the symmetric function g here. So we can use any symmetric function here for the G part, but especially for the PointNet that we are going to discuss here, we're going to use the max function as some kind of one of the symmetric function, right? But it doesn't need to be the max function, but we're going to also see what's some kind of the advantages of using the max function in this case. So you can say that the basic building block of this kind of the point cloud, the processing the neural network is basically having this form, that we are having the MLP, shared MLP, processing every single point, having some kind of the max pooling, aggregating all the information, and then processing them with another MLP. So this becomes a single, very simple the building block for some kind of the bigger neural network. And we can see that this kind of the one specific composition of the functions becomes another symmetric function. So we are achieving permutation invariance in this case. Make sense? Any question on this? So actually, you can say that like achieving the permutation invariance is kind of like doable. It's basically not very difficult. The problem is more in the basically transformation invariance. We want to basically see the results that we are basically getting the same output. However, we transform the given the point cloud like this. So these two should be the same bunny, whatever we do in terms of the transformation. But achieving this kind of the transformation invariance is very difficult problem. Actually, there are some kind of many kind of research in terms of how we can do this. But instead of like applying some kind of the fancy idea at the beginning, we are going to discuss some kind of very simple idea, which is about the spatial transformer. So basically, this spatial transformer is not the same with the typical transformer that we are talking about, right? So this is not the transformer architecture. This is about some kind of some specific the technique or some kind of the module in the neural network, which is not the transformer, the spatial transformer. But here, basically, the idea is that when you have some kind of given the point cloud, we are basically having some kind of small component in the neural network, which is basically automatically aligning the given point cloud into the certain pose. So that's the basic idea. So it might be good to show the kind of the figures in the next slide first. So actually, this idea has been introduced for the image processing first in the 2015, 10 years ago, and it has been adapted into the 3D the data processing as well in the PointNet case. So here, basically, the idea is that, let's say we want to do some kind of the classification of the traffic signs like this. See, so we are basically having tons of some kind of the images of the traffic signs, which might be taken from the very different views, different basically the skills and the orientations of the images. Then if you also train the neural network to classify those kind of the traffic designs, the basic idea is that we might need to basically have some tons of the images, right? Which are the photos, which are basically taken from all different some kind of camera angles. So here, basically, the idea is that we are first basically aligning this kind of the given images in terms of the scale and the orientation and the many things. In terms of that, we let the neural net to basically predict a transformation to align the image into some certain pose with a certain scale and some kind of the orientations, and then feeding this kind of some the corrected images, some rectified images as the input for the classification. And this becomes like more efficient in terms of that, we are not basically treating all the images as some kind of the different images, but we do some kind of some correction first, and then basically feeding some kind of the aligned images for the classification. So in terms of like the task of the classification, it becomes easier because we can expect that the first part of the neural net, the spatial transformer, will basically automatically align those images. So this is basically the basic idea. Obviously, you can see that there is no guarantee whether we will be really able to some kind of the perfect alignment of the images, but we are basically expecting the small neural network here will be able to predict some kind of the good transformation in terms of the like aligning all the images. So this is the basic idea for this spatial transformer. And the good thing of like having this architecture is that it's basically some plug-in architecture. So when you have some kind of any sort of the neural network, having some the bunch of the layers, you can basically plug in this small component at the very beginning in terms of that given the image, you first predict some kind of transformation, applying the transformation into the images, and then feeding this to the neural network. So this is basically some plug and play, some sort of the module you can easily plug into any architectures at the beginning of all the layers. So this is the basic idea for this spatial transformer, not the same with the transformer architectures. But do you have any questions on this? So yeah, you can see that as given the input here, based on the given input, we first basically predict like some scale and orientation. That becomes this part, like predicting the transformation, and then and then applying this transformation into the images and feeding this into the rest of the part of neural net. And the thing is that we can do the same thing for the 3D case as well. So that's the basic idea in terms of like achieving the transformation invariance. And now you can see that actually this is not really achieving transformation invariance. No guarantee. Actually, we are just like predicting the transformation in terms of that we're gonna get some kind of the alignment of the given the points. But actually, we don't know what sort of transformation that we're gonna get. But we are basically, expecting that the neural net will be able to get some kind of the align some kind of the point clouds. So what we do is that using the architecture of some kind of symmetric function. So we have seen like the basic building block of the the point cloud processing architectures, right? This kind of architecture having some small MLP, some pooling layer, the max pooling layer, and having another DMLP to get some kind of the final the outputs, right? So given this kind of the architecture, we can make some small neural network, which is now predicting 3x3 numbers, describing some kind of the 3D transformation, 3D rotations in this case. So we can basically have some kind of the 9-dimensional vector and then making it as kind of 3x3 matrix, right? And we hope that this network will be able to predict some kind of the good transformation, aligning any kind of the randomly oriented point cloud into some kind of certain the pose, right? And applying this transformation and then feeding some this kind of the transformed the point cloud as the input to the rest of the neural network. That's the basic idea. Are we applying the TNet before the bundle of PointNet? So yeah, we're gonna see. Actually, when we talk about the PointNet, which is the architecture which is involving this kind of the TNet. So you can see that actually this TNet is the small part of the entire the PointNet. Question? Any other questions? It is clear. So we are basically having a neural network predicting 3x3 matrix, and this becomes a rotation matrix and rotating the given the point cloud, and then doing some kind of the and then feeding this kind of rotated the point cloud as the input to the rest of the neural net. And here one question might be is that we are just like predicting 3x3 matrix, but how do we know that whether this is the really any rotation matrix or any random some kind of transformations? So obviously what we want to see is that we want to see that some rotated the rabbit here as kind of the same rabbit. Or if you basically like, scaling should be the same, but if you basically do some kind of make some more complicated some kind of deformations, then it should not be the same rabbit, right? So we want to say that actually some rotated divergence are basically the same point cloud. Otherwise, it's not making the point cloud, making some kind of the new point cloud. So which means that actually we want to basically only predict some kind of the rotation D matrix through this kind of T-net. But when we basically predict any arbitrary 3 by 3 matrix, how do we guarantee that this matrix becomes a rotation matrix? Right? Code T-net matrix shift the image. So yeah, we are not gonna discuss the translation here. So that's also kind of the limitation of the PointNet. We're also going to discuss the translation for the next architecture. Okay. So does it only have like 6 degrees of the freedom in such transformation? It depends on like how we define the transformation. For the rotation, how many degrees of freedom do we need for the 3D rotation? For the 3D rotation, actually, we need the 3 degrees of the freedom, right? We are actually going to get into some more details about this representation of the 3D rotations in the later the lectures. But basically, for the 3D rotation, we just need 3 numbers, like the Euler angles, to represent the rotations. But now, so we can do either basically not predicting 3 by 3 matrix, but predicting like some Euler angle kind of things, only 3 numbers. We can also consider predicting quaternions in terms of instead of the 3 by 3 matrix. So if we also have some time, we're going to also discuss the quaternion representation layer. So it depends, like how we represent the rotation of the matrix. The simplest idea that has been applied for the PointNet was that having this kind of the regularization in terms of like once you basically predict a 3 by 3 matrix here, then we are basically having this kind of a regularization loss in terms of that we are making this T matrix to be orthonormality matrix. So that's kind of some kind of the one simple trick in terms of making the rotation T matrix. Obviously, also this does not guarantee to make a rotation T matrix because we are just having some regularization D loss. It's not having some kind of the hard constraint, just like regularizing the output T matrix. There are also tons of the techniques in terms of like how we can really get some kind of the guaranteed the rotation T matrix. We are not gonna discuss like all the details here. Let's see whether we can discuss these details in the later. So the T-net can only rotate, not scale. It also depends. So we can also regularize the alpha matrix T to allow the scaling as well. So here we're gonna basically only consider that the T-net is only making some kind of rotation D matrix. We only care about the rotation invariance here. Any other questions? Can you also see what's the kind of the problem of like having dysregularization? Not only for that, it's just like not giving the hard constraint, but just regularizing. The problem of this regularization, I mean, many things. Obviously, this is not handling this scaling as well, right? So that's also kind of thing. We also don't care about this translation here as well. So translation is like one thing. Also, this is like regularizing this alpha matrix T to be orthonormality matrix. And are the only orthonormality matrices rotation matrices? Any cases that the orthonormality matrices become non-rotational matrices? If you took computer graphics course before. And what's the condition for a 3D rotation D matrix? So basically, the orthonormal matrix can be not a rotation D matrix, but also reflection matrix, making some kind of reflection, some kind of having the mirror and basically reflecting the things. So actually, the output also can be reflection D matrix as well. So in cases like when the reflection is you're just making a new shape, actually this is not sufficient deregularization for T, right? So basically, yeah, there are lots of the way in terms of like basically how we can really make some kind of basically output some rotation D matrix with some kind of guarantees. and how we can also achieve some kind of the rotation, the invariance, and also other types of the invariance as well. But this is some kind of the simple the idea in terms of that we are plugging in the TNet here, the specialty transformer, in terms of that we hope to see some kind of the automatic the alignment of the given the point cloud by just predicting some kind of the transformation here. And we specifically consider the rotation here. And then we are regularizing the output the matrix to be one of the rotation the matrix using this kind of regularization loss. So that's the basic idea. Does the TNet itself also needs to be permutation invariant? Well, I mean, we are not predicting this the transformation not for every single the point, but also for the entire the point clouds. So that's the kind of thing. And yeah, and also obviously, yeah, the TNet should be permutation invariant, obviously. Yeah. So as the TNet, we are using the simple the building block that we discussed before, the having the symmetric functions and the compositions of the MLP and the max pooling. Yeah, obviously, it should be the permutation invariant. Yeah. Any other questions? If the TNet is transforming the data, what is the transformation block doing? Well, I mean, so as I said, like, once the TNet predicts the transformation, which is we hope to be a rotation D matrix in this 3D space, we apply this rotation to all the points into the given the points here, and then getting some kind of the rotated points here. And then now also feeding these rotated points as to the next layers. Is this clear? Transformation, this is not any kind of the neural network. This is just like applying the transformation to the points. TNet is a pre-trained model? No, we also train the TNet simultaneously with all the other layers. So that's those kind of thing. So that's the kind of the interesting part of the spatial transformer in terms of that we do not basically train this kind of the some alignment layer separately, but we hope to basically train all of the layers jointly while hoping that this TNet will play the role as doing some kind of the automatic alignment. But obviously, that said, there is no guarantee whether this will really align all the kind of the images and also point clouds. So we're gonna have the first assignment, which is implementing the PointNet, and you will see how much this like TNet will be helpful. Actually, there are lots of, yeah, we'll see. Doesn't the TNet needs to be permutation? Yeah, the TNet should be permutation invariant. Yeah, all the layers that we are going to see here should be permutation invariant. So as I said, like we are having this block for all the layers. Right? So let's see, like layer by layer, given some kind of the n by 3, the point cloud, it doesn't need to be n by 3, as I said, like it can be x, y, z plus like RGB or like surface number, many other information. So let's say if we only have the x, y, z here, n by 3, the kind of the 2D layers, 2D arrays, then we are basically having the TNet in terms of basically applying some kind of transformation and getting some kind of the transformed, the rotated, the point cloud here. And then we're gonna keep applying the same the building block in terms of like increasing the dimension for each of the points. So here basically is nothing but just like having the shared MLP for each of the points, increasing the dimension to 64. And also what we are going to do is that even for those kind of the points in the higher dimensional space, so now we are having some kind of some features for each of the point, right? So 64 dimensional features. So for those kind of the point cloud also defined in the higher dimension of the space, we can also do the same thing. We can also apply the TNet, predicting some kind of transformation and doing some kind of applying some sort of the rotation in the 64 dimensional space. This is basically nothing but just doing the same thing, not in the 3D space, but also in the 64 dimensional space. So yeah, we are going to do this kind of another kind of the alignment the 64 dimensional space again as well. So getting these kind of things. And then having some kind of the multiple the MLP layers in terms of we are processing every single point independently, but using some kind of the same function, the same MLP function for all the points. And to make this kind of permutation the invariant, we are going to apply the max pooling here getting some kind of globality features. And as I mentioned in the previous slide, we're also going to do some kind of post-processing using the set of the MLP layers and getting some kind of the final, some kind of the scores for each of the kind of class D labels. So this becomes the basic the architecture for the PointNet the classification the network. It is clear. So you can see that except for the TNet part here, the whole thing becomes that we are basically first applying the MLP for each of the point in terms of basically increasing the feature dimension into the 1024, applying the max point here, this symmetric function here, and applying some kind of post processing the MLP in terms of getting some kind of the output discourse. So here the question is that when applying for transformation, how do we know current state? How much is rotated? Well, I mean, the output will be very explicit rotation in the matrix. As the output of the TNet, we are getting the 3 by 3 matrix here and also 64 by 60 matrix here. We just directly multiply this matrix to the points. Clear? Why do we need additional TNet? So, I mean, this is not necessary. I mean, this basically additional the alignment is not necessary. This is basically some kind of the further alignment that may not be basically really controlled by the first part. I'm just like showing that we can do this kind of some automatic alignment not only in the three-dimensional space here, but also in the higher dimensional space as well. And we basically have seen this kind of some architecture, which is like having the two adjustment. But actually, you can see that without like one of them, actually it works kind of okay. Actually, even without any of these, actually it's kind of okay for especially for the cases that when the points are really quite well aligned. So yeah, so we'll see. We have a airplane shape rotated by 0 degrees, 30 degrees, and does the TNet predict the matrix to rotate these shapes into the, for example? So the good question is that when you have the airplanes rotated with the 0 degree, 30 degree, or the 90 degrees, does the TNet predict the matrix to rotate this shape into the shape at the 30-degree rotation? So the thing is that we don't know what the kind of transformation that the TNet will basically predict. But we just hope that the TNet will basically predict some rotation, which is rotating like whatever some kind of the rotated the shapes into some kind of the consistent kind of pose. So after applying the TNet, we don't know whether all the point clouds will be rotated 45 degrees or the 30 degrees or whatever. But we just like hope that this TNet will basically align this kind of the points in terms of their pose into the certain rotation. And the kind of the reason why we're having this kind of expectation is that when we see that all the points are basically aligned well, then the rest of the part, the classification, the task will become way easier, right? So there is no kind of like theoretical guarantee, but we hope that the neural net will be, the TNet will be trained in a way that it is making the training of the rest of the part of the neural net becomes easy. So that's the basic idea. Okay. Yeah, obviously there might be some kind of mysteries here, but the problem here is that there's no any kind of theoretical guarantees here. So you're gonna actually will be able to implement this yourself and see how much this works. So there are also lots of the issues with this. But this is some kind of the very simple the idea in terms of that we are trying to achieve some kind of the rotation, not exactly achieving rotation invariance, but we are basically removing this kind of the factors of the rotations in terms of the some training some kind of the neural networks. Okay. So you can see that this like whole kind of the big architecture is actually can be simplified into can be understood into this form in terms of we are having the MLP running for each of the point independently, but shared MLP, same MLP, having the max plane here, and then doing some kind of post processing. So we can basically make some kind of the architecture as the symmetric through this kind of the architectures. Makes sense. And you can see that actually this is for the classification. So as the output, we are getting some kind of the some output discourse for the entire the point cloud. And as I mentioned before, for the segmentation, we might also want to get some kind of the some outputs, not for the entire shape, but for each of the point, right? So here the question is that how can you get some kind of the per point outputs from this architecture? Or more specifically, how can you consider combining some kind of the global information here at some point, some kind of global features with some kind of the local information here? In terms of the, at the end, we are getting some kind of the per point outputs. Any ideas for this? Yeah, as you said, like this, the simple idea is that it's nothing but like, you can say that actually this is the 64-dimensional feature for each of the point, right? For every single the feature for each of the point, we simply just like concatenate this global feature in terms of that the long feature here, the concatenated feature has some information about the every single point, but also the entire the shape. And the rest of the part is basically also the running the NLP for each of the, some kind of the per point features. So in terms of that, we can also get some kind of the output scores, not for the entire shape, but for each of the point as well. Makes sense? So this is like simple the idea in terms of that we are extending the PointNet, the classification the architecture for the segmentation the architecture as well. So yeah, this is the segmentation architecture. It's quite simple. And previously the question is that there was a question like, can I think of the aligning the features as the aligning small part of the point cloud? So I guess the question is about this part, like aligning the features is actually not aligning small part of the point cloud. So now it's still aligning the entire the point cloud, but not in the three-dimensional space, but just in a like higher dimensional space. So this is nothing but now we are representing each of the point, not with the three numbers, but with some kind of the more numbers, but 64 numbers, right? So in terms of that, now we can see that every single point is present at the 64-dimensional space. And we can think about the like point cloud in the 64-dimensional space. That's basically the point cloud in the features the space. And what we want to do is that for the point cloud in the 3D space, basically they might have some kind of different sort of the rotations in the higher dimension space as well. And we also do some kind of the alignment in this kind of the 64-dimensional space as well. But this is still some kind of the global the alignment, not the partial alignment. So that's the idea here. Any questions on this? So this is the simplest architecture in terms of that we can basically process the given the points while basically guaranteeing the permutation invariance for the classification and also the permutation equivariance for the segmentation here. As you can see, if we basically permute the order of the points here, obviously the permute the order of the points here will be also changed. So we can also achieve some kind of permutation equivariance here. And we are not guaranteeing, but basically somehow enforcing some kind of the some kind of the rotation, the alignment through the TNet, the special transformer here and here. So that's the basic architecture. And you can see that actually this is like very simple architecture. You see that actually the implementation of like this whole architecture is like few number of the lines. So in terms of that, it's really efficient. And also we is gonna discuss the efficiency of the architecture later. But any questions on this? So yeah, so if I introduce some of the applications, especially some kind of the toy, some kind of the setup that we can basically easily test the performance of the some 3D neural network. There is basically a data set called the ModelNet, which is also like more than like 10 years old, the benchmark, which is also for some kind of classification task. So this is the case that we are having the 12,000 some CAD models and having the 40 classes. So we can train the neural net with some kind of some portion of the training, basically the training set here, and testing with the performance. And we can see whether the neural network can properly classify all the shape into these like the 40 the classes. So as we have some kind of Cypher 10 or the ImageNet for the image cases, the model net is basically the very simple kind of the benchmark that we can test the performance of the classification of some 3D neural network. And if we see the output, the interesting thing is that, so actually this second row, this whole row, is basically the neural network, which is directly taking the voxels as the input. So these are basically the architectures which is using the 3D convolution of the neural net. And having the accuracy of the more or less like 89% here, right? And the other basically the architecture is the second part, the third part actually. So these are the multi-view based some kind of representations, taking the multi-view images as the input and using the 2D convolutional neural network, right? Achieving the classification accuracy was like 90 here. So before the classification accuracy was like 86. And compared to that, the PointNet is also achieving the accuracy of the 86 like this. So you might see that actually, yeah, the accuracy is kind of the same. But the big difference is that this is the second row here. This is the case that we are representing all the shapes with the 30 by 30 by 30 the resolution of the voxels, which is still like very low the resolution. You can see that compared to images, 30 by 30 by 30 is very low resolution, right? Still, it will basically have some kind of the 27,000 of the numbers. So every single the shape is represented with the 27,000 of numbers. So which means that it's kind of like heavy, still very sort of the heavy representations for the single shape. How about the multi-view images? For the multi-view images, so this is the case that we are taking 80 images, 80 views. And every image is basically having the resolution of the 164 by 164. And also each of the pixels will have the RGB, the three numbers, right? So this means that each shape is now represented with the 164 by 164 by 3 multiplied by 80. So more than 6 million numbers. It's very heavy representation for a single 3D object, especially even compared to the 3D the voxels as well. Compared to these two cases, the PointNet is just using 1024 points, and every point is having the XYZ coordinates. So the 3D object is now represented with just like 3,000 numbers. So you can see that this is like way more like basically the compact representation compared to these two, while we are basically achieving almost the same accuracy for the classification and also the segmentation. So you can see that actually the compactness wise, the point cloud is way more the compact here. So which means that we can achieve some kind of the same accuracy with some very few number of the kind of the numbers here. And also the architecture also becomes way lighter than the other representations, especially compared to the MVCNN, which is taking the multi-view images, having 60 million the parameters for the neural network. The PointNet is just having some kind of the 3.5 million the kind of the parameters, which is like way smaller. So you can see that actually the point cloud encoder is very efficient and also the effective architectures compared to the neural network that is taking other representations. Clear? So this can be especially good for some kind of some mobile devices or some kind of cases that we cannot have some kind of very heavy architectures. And also for the segmentation, the kind of the very the basic the benchmark is the ShapeNet the data set, which is also having the 16 the classes with the 16,000 the shapes, and each of the objects is having 2 to 5 the part labels. So you can see that these are some kind of the part labels for all these 3D shapes. And the total number of the part labels for all the 16 the classes is more or less the 50. So we're having the 50 the part labels. And for those cases, we can basically train the PointNet and get this kind of some segmentation results. So these are actually the output of the PointNet segmentation. And another like more the complicated some kind of a setup is the scene segmentation. So this is also the case that we are now taking the point cloud of some kind of indoor scenes and segmenting them into the chairs and the tables and walls and many other things. So these are also some kind of the scene segmentation results. And typically what we do for this kind of scene segmentation is that obviously the number of the points for the scene will be very huge. Will be like more than like a million. So we are basically having a million of the points here. So since a million of the points might be too big to just directly feed into the the neural network, what we do is that we basically crop the point cloud into some certain region and feeding them into each of the region into the neural net, and then integrating the outputs, the pointed outputs for each of the region into the entire scene. So this is kind of the results for that. And this is also the results that we achieved like 2017, like 8 years ago. So now we have some better GPUs that has some more D memory. So we can consider basically just directly feeding entire the points into the GPUs. But yeah, so this is some kind of ideas for this. Some results with the part segmentation for the ShapeNet, for the parts in the objects, and also for the objects in the scene. Yeah, here the IOU basically means the intersection over union. So this basically means that if you have a predicted segment and the ground truth segment, so ground truth basically means some kind of the correct answer for the segmentation. So if we have some kind of the ground truth the segment and the predicted segment, we basically measure the intersection over union, the ratio of the points that are basically intersected with these two segments over the union of the 2 points, and basically measuring this kind of ratio here. So that's the IOU. How do we define portable? Well, I mean, yeah, so basically means that we can basically these architectures do not require that much kind of the memory. So for the cases that we cannot have some kind of the big GPUs, but very some kind of some small GPUs with the small D memory, we can still try to adapt this kind of architectures. Just talking about some kind of the efficiencies of the architectures. Clear? Any questions on this? So we can say that actually the PointNet is good in terms of the efficiency, and also it can basically run with some kind of a small number of the points with some kind of good accuracy. But actually, there are some kind of the moldy analysis in terms of like why it's basically good in terms of the and also robust in terms of the data the corruption. So what this data basically shows that let's say we are basically achieving some kind of the classification the accuracy of the like 86 or something here, and we are basically seeing like even when you remove some of the points, when you drop some of the points in the given the point cloud in the test time, how much accuracy that we can still get. See, so let's say like we train the PointNet with the 1024 the points every single time, and the test time train the PointNet with the 1024 points, and in the test time we are basically dropping some of the points, not using all the 1024 points, but using a subset of the points. So this is the ratio of the dropping the points. So let's say we drop the 20% of the points, 40% of the points, even 60% and 80% of the points. How much the accuracy basically drops, depending on the missing the points. And the thing is that surprisingly, even when you only have the 80% of the points, randomly dropping the 80% of the points in the test time, we still just get the 20% of the accuracy drop. It means that it's almost the same accuracy, right? So this is really good in terms of the even when you lose lots of the information from the given the point cloud, actually we are getting some kind of the okay the accuracy, which is really different with some kind of the previous architecture using the 3D convolutional neural net. For the cases that we are using the 3D convolutional neural net, if we drop the 80% of the information, then we also see that the accuracy also drops into the 80% like this. So here the question is that how can he, achieve this kind of the robustness with the PointNet, and what's the reason for that? We are basically having this kind of the results that not losing the accuracy even for the lots of the missing points. Can you guess like why we are having this kind of the robustness with the PointNet? Why is PointNet good at basically missing point? Any thoughts on this? So we can think about this architecture again. Yeah, so if we think about this architecture, that we are having some kind of the features for each of the point using the shared NLP here and max proof the global feature. Then basically we are going to feed this kind of the global feature for the classification at the end, right? Then what we can see here is that before the global, the max pooling here, we're gonna have the 2D array, which is for the 1024 points with the 1024 dimension. And then the max pooling here basically means that for every dimension for the features here, we are taking the max value, taking max value here, taking max value here, taking max value here for every dimension along the features, right? The feature dimension. And which means that we are taking the number, which is the maximum across all the 1024 points. So every full dimension, there will be only one point, which is contributing to get the final, the max number. Then what we can see is that, let's say like we say the point, which is contributing to the max, the number in the max pooling for every dimension as kind of one of the critical point. Can you see the meaning of this? So for each dimension of the features here, we're gonna pick the max number. If the max number comes from the the order of the point, we're gonna take this as kind of one of the critical point. So which means that for each dimension, we will be able to basically select the critical point. So the maximum number of the critical point will be 1024 because we're having 1024, but there can be one point which is basically contributing to the multiple axes, multiple dimensions, right? So actually, if we visualize only the critical points, you can see that actually the critical points are basically properly capturing some kind of the characteristics of the shape, right? So for example, like when you basically do some kind of the classification, whether this is the the lamp or the table here, these kind of the points on the edges or some kind of the edges here will be some kind of the important points to basically see the shape of the given the point cloud, right? And actually we can see that not all the points, but some points on some kind of the edges are naturally giving some kind of the, those are some kind of points that are giving some kind of the important information for the classification, right? And we can see that those points are selected as the critical points in the max pooling. So which means that if we have like only this kind of the subset of the points, if we only have a set of the critical points, even when we lose any of the points outside of the critical points, we're gonna get the same result. Make sense? So even when you have the 1024 points, there will be very small the subset of the points that become the critical points that are basically giving the max number for every dimension of the features. And if we only have this kind of the subset of the points, we're gonna get the same results. Which means that even when you lose any of the sum of the points that are not included in the critical point, we're gonna basically get the same the outputs. So that's basically the reason for that, like why we are basically achieving some kind of the high accuracy, even when you lose some of the points in the given the point cloud. So if the points that we are losing are not one of the points in the critical set, that will not affect in the final result. Make sense? So if we also talk about some kind of the upper bounds, so the upper bounds are basically some of the points that are basically not affecting to the final the outputs. So we can think about that we are querying any kind of random points in this 3D space and basically include these points if they are basically not affecting to the final the outputs, which means that the number of the dimension of the features are not basically higher than the maximum number that we are taking in the global features, right? For those cases, if we take any kind of so these are some kind of the visualization of the upper bound, right? So even when you basically lose any of the points in the shape, the given the point cloud that are not included in the critical of the point, well, when you basically add any kind of the points that are included in the upper bound set, that will not basically affect the final the outputs, which means that there are basically have some very small set of the points that are really affecting the final the outputs. So when you basically corrupt the given the point cloud in terms of losing some of the points or adding some kind of new points that are not really affecting to the final the global feature, the output will not be changed. So that's kind of some key reason for that why we can achieve some kind of the high the robustness with the PointNet. In the graph, there is a farthest line, so they drop the points which are not critical points. Then if all the points are, then which points are dropped? I couldn't really get the meaning of the last question. So basically, if we start to lose some of the points in the critical points, then obviously that will affect the final results. But you can see that still there are lots of the points that are not really affecting to the final points, the final results. So that's kind of the key reason for the robustness. And even when you also lose some of the critical points, still just losing just a few of them will not make some kind of the big impact. So that's kind of the reason. So you can see that like this is actually reason like why we are using the max pooling instead of the sum or the average or the many other things. So if you basically switch the symmetric function from the max function to the average or the sum or any other things, then we will not be able to achieve this kind of property. So you can also check out how much the robustness is basically being changed depending on the choice of the symmetric function in your the assignment. Depth basically means just kind of distance from the camera to the each of the point. So the color basically encoding some kind of the distance from the camera to the point. So we are now running out of time. So I'm going to continue the other some kind of the more advanced the point cloud encoder next time. And then after that, next Wednesday, we're gonna have the TA session for the assignment 1, which will be about implementing the PointNet and also some other the advanced architectures. So I'm going to see you next Monday. And if you also have some more questions, please post those questions on Slack. We will be able to discuss your questions on Slack. Okay, and I will see you next Monday. Thank you.